I'm going to show you guys how Giotto can interoperate with other frameworks such as Seurat, Data, and Spatial Experiment Object. To start with, we are going to first load the Giotto object. That would be a Giotto mini Visium object. And then we will proceed with the conversions that would be the Seurat, Giotto to Seurat, and Spatial Experiment and Data. So, first of all, we load the required libraries that are needed for the for loading the Giotto mini Visium object. That would be Giotto and Giotto data. Now we use the function load Giotto mini, and for the sake of this workshop, I'm only using the Visium object. So we have a Giotto mini Visium object now. We can see the Giotto mini Visium object as well. For the Seurat part, actually we have 4 tailored functions. That is Giotto to Seurat version for the Giotto version 4 and Giotto version 5. For the Giotto to Seurat version 4, we have so for version 4 we have Giotto to Seurat version 4 and Seurat to Giotto version 4. And for the version 5, we have Giotto to Seurat version 5 and Seurat to Giotto version 5. Since the Seurat version 5.9 now includes subcellular and image information in it. And we can see it here that how Giotto and Seurat are mapped onto each other. So for the Seurat to Giotto functions, the S's are mapped on the expressions, and for each spatial unit, Seurat has a separate object. The dimension reductions and spatial locations goes to the reduction slot, and the nearest network and spatial network goes to the graph slots. Now, for the next part, we are going to go further with the conversions of the Giotto object to Seurat object, and for that reason, this part would include libraries Seurat, ggplot2, and patchwork. So once we have all these libraries loaded, we can use the function Giotto to Seurat version 5. That would for the workshop we are only converting the Giotto object to version 5. If you guys want to run it for version 4, you guys can do that too. For Giotto to Seurat version 4, we use the Giotto object and spatial unit SL, which is the default spatial unit, and we have this Giotto object being converted into Seurat object. Now we do some plotting in Seurat and see the volume plot and spatial feature plot using the N-count RNA features. So here we can actually visualize these two together. This is the volume plot, and this one is the spatial feature plot of the Seurat. That is the function from Seurat. And since this Giotto object has 2 images that are alignment and image, both of these are being plotted here. Okay, so now we run the SCT transform on the Seurat object that we converted from the Giotto object. And after running this SC transform on the Giotto Seurat object, we will have another SA in Seurat that would be SCT SA. And I will be for the downstream analysis with Giotto object, I will be using RNA only. If you want to use SCT, you can use that as well. So here, since the RNA assay do not have variable features in it, while the SCT has, so you do not have to find variable features for the SCT. For the RNA, you will have to run this function as well. And then we will find the run PCA function of Seurat to find the PCAs of an object. And now we run the function find neighbors and UMAP. So we have calculated the UMAP, and we have run the component analysis using the Seurat. And now we are going to plot this UMAP in Giotto object. So for that reason, we first need to convert this Seurat object back to Giotto object. And to do that, we have to actually specify that which of the reductions are dim reductions and which of them and the networks are spatial networks or nearest networks, since in this figure I have already shown that the dimension reductions and spatial locations both goes into the reduction slots of the Seurat, since Seurat do not have separate slots for spatial location and dim reductions. And exactly for the NN network and spatial network, both of these goes to the graph slots of the Seurat. So when we convert the Seurat object back to Giotto object, we need to specify which of these graphs or reductions are actually the dimension reductions or nearest network or spatial network. So here I'm specifying the dim reductions as PCA and UMAP, Delaunay network, and then SNN, PCA, and custom NN. So now we have a Giotto object that we created from Seurat object, and we can see that the spatial network that we gave as an input for the Seurat object is the Delaunay network only, while the original Giotto object has different more of them, since like spatial network and Delaunay networks as well. I gave only Delaunay network. You can give more than one networks in it. So going further, so I also would want to show you that we can actually do this for GS for the SCT essay as well. So for Seurat to Giotto and spatial essay as SCT, and that would create a Giotto Seurat object that would have a city in it. But that wouldn't include any dimension reduction spatial network or nearest network, since I haven't given them as an input here. Argument says. So since I have the Giotto object with me right now, now I can do the clustering in Giotto object using the function do k-means clustering. So we can visualize, we can see that where actually is the k-mean stored. It is stored into the cell metadata column, which is k-means. So now we plot this UMAP using the function plot UMAP, that is the function in Giotto. So here I can show you. This is the output of this UMAP that actually we can calculate it into the Seurat object and converted that Seurat object to Giotto object and plotted this UMAP using Giotto's function. We can actually run binspect on it as well, since binspect is binary spatial extraction of genes and is actually very fast computational method that identifies gene with spatial coherent expression pattern. So it runs, it returns a data table. I can show you guys here. This is the data table that it returns with p-value estimate and then number of connections or interactions a feature has in the near network analysis. It has adjusted p-value and scores, average expression, and highest expressions. Next, we can use the function. So now we can have the first top 300 spatially significant genes based on this ranking criterion. So if we run this, we will have 300 genes that are the top genes. Now we can we can use this detect spatial correlated features function that would actually detect the correlated features within this specific network. Here I'm using the Delaunay network. So, and this Delaunay network is the one that we got from this Seurat, right? So now we can actually show that using the heat map function. So here I cluster the spatial correlated features, and then I use heat map function that actually plots the heat map. Okay. So next part is the conversion of Giotto object to spatial experiment object. Since the spatial experiment object is the data container, has the data container that handles data from spatial omic experiments, and it includes coordinates, images, and metadata. So Giotto Suites provides Giotto to spatial experiment and then spatial experiment to Giotto, and these are actually mapped onto each other in a way where for each spatial unit, spatial experiment would have a separate object. So when we convert the Giotto object to spatial experiment object, it returns a list of spatial experiment object for each spatial unit. So we go there. So for this part of the interoperability, we need to have spatial experiment library and an SVG, since we are going to show how we can get the top features from using NNSVG, and then we will plot those top features in Giotto. So we load the required libraries, and then we use the function Giotto to spatial experiment that would convert the Giotto object to the Giotto spatial experiment, a list of spatial experiment objects. So here we have a list of Giotto spatial experiment objects. If you see, since VZM has only one spatial unit, there is only one object in it. For the VisGen, it would have 3 in it. So we get the first one and run the NNSVG on it. So in order to run the NNSVG on it, we need to have the one assay should be like named as log counts. So first of all, we look at the names of the SPE assays, that is normalized RNA assay, scaled assay, or and RNA cell. We are going to rename this normalized RNA cell into log counts. So do that, and now we can see that it's been renamed. Now we run the lead-in clustering on it. For this purpose, we are going to have the lead-in clustering. So here it is. Now we run the NNSVG on it. Since the NNSVG part actually takes a lot of time, we will. I have uploaded the data on the Zenodo as well. You can get it using the link that I have posted here. So I will just like show that this function works, but I'm going to load it from here, and we have it. So now we see the top 10 features that we got using the function in an SVG, and these are the top 10 features that we get. And now we convert that spatial experiment object to Giotto object and plot these features. So this is the function spatial experiment to Giotto that would convert the spatial experiment object to Giotto object. We can print this as well and see what it has in it. So for the so now we use the get feature metadata that would actually have the metadata for all features and store it as a data table. So we can see it here. So this is how we get this. And now we get the first 10 top 10 features that this data table have. And these are the top 10 features in Giotto object. And these are the exactly same that we calculated using the NNSVG. Now we calculate these in Giotto. Plot these in Giotto using the spat feed plot 2D, and this is how it turns out. This is how it turns out. So I gave only the first 4. You can give more than these or less than these. Now for the end data, we have for the back and forth conversion of Giotto object, we have end data to Giotto and Giotto to end data. It actually, you can see it here, that the spatial for each spatial experiment object, and that actually has the same thing, that it does not support the hierarchical structure like the Giotto, and thus the for each spatial unit it will have a different ended object, and this is how the slots are being mapped onto each other. And so images right now are not mapped between these two classes, and so to start with it, we will first have to have end data and like reticulate in our session. And once we have these, we will actually also specify the result directory, because we would want this end data file to be stored somewhere where we can like get it back to convert to, so we can like retrieve it. So this is the results direct. So you can like add so for the end data, you need to have the KNN network. Since Giotto has a default NN network in it, so we will use KNN. We will first create a nearest network using KNN as the type. Now we convert the Giotto object to end data object using the function Giotto to end data, and we also specify the directory where we want to store this Giotto object. And this is our ended object. This when we actually try to print that Giotto object, we ended object, we will also get the directory where it's been stored. So it's easier that way. I have like also uploaded this on the Zenodo, where there is where it's like Zenodo that shows where the this .h580 file where it's been created from Giotto. So now we use scanpy to go for the pre-processing steps in the ended object. For scanpy, we will import scanpy, and now we to read the h580 file, we will give the path to h580 file, which is here. So for this part, I will have it. Yeah. So we can see that this H580 file has been read, and now we use the scanpy to normalize the total counts per cell, and to log transform the data, as well as to perform PCA, and to find the neighbors. And it also now we also use the UMAP to run UMAP on it, and now we need to store this and data object that is being processed using scanpy. We can do it using the scanpy function, right? So now we stored this first file that we have written into another variable that I would name as this. And now we convert this processed file that is being processed using the scanpy back to Giotto object. And for this reason, we will just do this. So this is the ended object that we created using Giotto from ended to Giotto. And now we use the UMAP to visualize the ended object. The Giotto object that we created using ended. So I'm using the prot UMAP function from Giotto, and this is the outcome. This is the outcome. And now we so now I'm just going to show you guys how Giotto how ended could have like multiple, and how Giotto can create multiple ended objects or spatial experiment objects, since depending on the spatial units. So since the vision object has more than one spatial unit, so you can see it here that mini Giotto object has 3 spatial units, that is Z0, Z1, and aggregate. And if I convert it into first we need to obviously have to calculate the KNN network for to if we want to convert it into N data. And once we have that, we can convert it back to, we can convert it into N data. And once we create into N data, we will have three different Giotto objects. So here we have three different Giotto objects. For spatial unit Z0, we have separate N data. And then for spatial unit Z1, we have another N data. And then we have for the aggregate one. So if we just print this, we will get the locations of these files on the N data one. N data files on where they are being stored. So that is it from my side. Thank you.